Okay, calculus, let's do 13.6, directional derivatives in any direction. So up to this point, we've done partial derivatives for x and y, which gives you the direction directly in the derivative in the direct x direction and direct y direction. But we can use those two things to get a derivative in any direction. It basically boils down to this. No matter what direction you're going, a certain percentage of it is going to be in the x direction, and a certain percentage of it is going to be in the y direction based on the angle of the direction you're traveling. Now, how do we normally convert angles in terms of x and y directions? We usually use cosine and sine. So generally speaking, if we were doing a parametric equation for, say, this curve, traveling on the line, you'd say x will be anything along the line x naught plus t cosine theta. Y would be anything along the line y naught plus t sine theta. And cosine and sine work out really nicely because they don't change the magnitude of the direction you're moving, because cosine squared plus sine squared is 1. So if we look at going from the point x naught, y naught, f of x naught, y naught, to xy, f of xy, we can look at a few equations and how they change on page 2. The distance formula is still the absolute value of t, which is what we want. The slope of the secant line can be written, and by letting t approach 0, you can arrive at the derivative. So the definition of the directional derivative: f is a function of two variables, x and y, and you let u equal cosine theta I plus sine theta j be a unit vector, and the directional derivative of f in the direction of u, denoted by du of f, is du of f of xy. The limit as t goes to 0 of f of x plus t cosine theta y plus t sine theta minus f of xy all over t. Calculating directional derivatives is similar to finding a derivative of a function of one variable by the limit process. However, a simple formula can be used to find this because we don't want to necessarily use the limit from definition. If f is a differentiable function of x and y, then the directional derivatives of f in the direction of the unit vector u is du of f of xy is the x partial derivative of xy times cosine theta plus the y partial derivative times sine theta. Now, of course, just like there are infinitely many different angles, there are infinitely many different directional derivatives on a surface, because a point, if you're on a hill, let's say even at the top of a hill, you could travel down the hill, if it's a 360 degree, in any direction. So your slope may be different in every direction. So that the idea is there are infinitely many directional derivatives, and this theta is going to determine the direction you're going and will affect the magnitude as a result. So let's start off with some basics. Okay, so as we discussed already, if we take theta to be 0, we would have cosines of 0 times I plus sine of 0 times j, but sine of 0 is 0, so it's just I, and that's just the x direction, the positive x direction. Similarly, if you let theta equal pi over 2, that's the positive y direction. So let's see how this works in a math problem. Find the directional derivative of the function f of xy equals 4 minus x squared minus 1/4 y squared at the point 1, 2 in the direction of the unit vector cosine pi over 3 I plus sine pi over 3 j. So that's at an angular direction of pi over 3. So first things first, we need to find both partial derivatives. So the partial derivative with respect to x, these are constants in terms of x, so this should just be negative 2x. Partial derivative in terms of, or with respect to y, this is the only part that matters, it'll be negative 1/2 y. Now, it says it wants it at the point 1, 2. So at the point 1, 2, that means x is 1. This would be negative 2. This is 2. This is negative 1. Now I need to take those and multiply them by their corresponding unit vector portion. So du of f of 1, 2, where u is this direction, is now negative 2 is my x component, so it's going to be times the cosine of pi over 3 I, minus 1, my y component, times the sine of pi over 3 j. What's the cosine of pi over 3? 1/2. So negative 2 times 1/2 minus 1. So what's the sine of pi over 3? Root 3 over 2. So this would be negative 1 minus root 3 over 2. It's approximately negative 1.8. If you're going to round to a decimal, I would prefer to use that answer up there. So it's saying that the directional slope at that angle going down this picture hill is about negative 1.8. So this leads us to the next thing, the gradient. The gradient of a function of two variables is a vectored value function of those two variables. The definition, let z be a function of x and y such that they both partial derivatives exist, and the gradient of f, denoted by what looks like an upside down triangle, is the vector partial derivative of x times I plus partial derivative of y times j. The symbol is read as delta f. Another notation for the gradient is given by grad. So you may see either of these notations. It's a vector in the plane, not necessarily a vector in space. We may get to space in a second. So how does this work in a problem? It really is just about finding the partial derivatives. So find the gradient f of xy, or find the gradient for the function f of xy equals y ln of x plus xy squared at the point 1, 2. So again, I need to find both directional derivatives at the point, and they simply will go with I and j. So let's do the partial derivative with respect to x. Y is a constant. The derivative of ln of x should be 1 over x. The derivative of xy squared should just be y squared. The partial with respect to y is ln of x plus 2xy. Now we're doing it at the point 1, 2. So we've got 2 over 1 plus 2 squared, which is 6. For y, we've got the ln of 1 plus 2 times 1 times 2. That's 0 plus 4. This is 4. Now, all we do here is the x partial derivative goes with the y, or goes with I, the unit vector in the x direction. The y partial derivative goes with j, the unit vector in the y direction. So my gradient of f is 6i plus 4j at the point 1, 2. Now, because the gradient itself is a vector, you can write the directional derivative in the direction of u as the dot product of the gradient and the direction vector, because the gradient's components are going to go with the direction vector's components when that 6 would be multiplied by the direction plus the 4 multiplied by another direction. That would make a dot product. So the last theorem on this page is if f is a differentiable function of x and y, and the directional derivative of f in the direction of the unit vector u is du of f of xy is the gradient of f of xy dot product of that in the unit vector u. And we'll explore how this affects us more in the next video.